We are from Group 12. We are going to present you about the cryptography. It's about the members. So there is Fatin, Adani, Binti, Ahmad, Taufiq. Me, myself, Fatin, Aleya, Binti, Fakarudin. And also the third member is Sofea, Amiera, Binti, Remeli. Meaning of cryptography. So cryptography, which is both an art and a science, deal with technique for encoding and decoding messages that are exchanged between two parties. In the language of cryptography, codes are called the cipher, non-coded messages are called plain text, and coded messages are called ciphertext. The main reason for the use of cryptography is to communicate with another person without allowing access to anyone outside the party. To do so, party members use some sort of algorithm to make their message unreadable to everyone except for them. Okay, so next moving on for the example in real life of cryptography. So the first one is in secure online communication, which is in messaging apps like WhatsApp and Telegram. Use end-to-end encryption to ensure that the only sender and receiver can access the message. The encryption technique scrambles the message during transmission, making it unreadable for third parties. And the second one is the banking and online payment. Okay, so ATM and credit card have the pins, and the pins are encrypted when entered into ATMs or payment devices to prevent unauthorized access, such as the PayPal, Apple Pay, and also Google Pay use the cryptography techniques to secure the transaction data. And the third one is for identity verification. So the cryptography allows the use of the digital signature to authenticate the validity of electronic document, email, and also the contract. So this is crucial in sectors such as real estate, law, and also the e-commerce share. Okay, so other than that, it is also in biometric authentication, which is the system that use the fingerprint and also the facial recognition and also iris scan frequently use the cryptography technique to secure, store, and match biometric information. Moving on to the next section, which is encoding by using 2x2 matrix, by using the matrix addition and also the subtraction. This is the decoding word into numbers, the space, and also the alphabet from A to Z. A as 1, B as 2, C as 3, and so on until Z as the 26. Okay, so for the next slide, using the decoding word, the word mat is arranged in the 2x2 matrix and it becomes 30, 1, 20, and 1. And this matrix is minus with the random key BLCB, which is when converted into the matrix, it would be 2, 12, 3, and 2. And the sum of the addition matrix, the word mat, and also the random key would resulted as 50, 30, 23, and 3. And this addition would read as OMWC, and we can get the mat again when we subtracting the sum from the addition that we obtained before with the random key, and we will get the word mat again.
So I will be representing on encoding and decoding messages using 2x2 matrices. In this session, we will discuss on how to apply matrix transformation to encode and decode data. This involves concepts such as matrix multiplication and the adjoint method for finding inverse for message representation. So the first step that we need to do is to define the matrices. The encoded matrix E is a 2x2 matrix given as 4, -5, 2, and 0. And in order to decode the message, we need to find the inverse of this decoded matrix using the formula 1 over determinant multiplied by its adjoint. So the first step, for the determinant, we will have to multiply 4 with 0 minus -5 with 2, which will give us the answer of 10. And the inverse matrix or the decoder matrix is 0, 1 over 2, negative 1 over 5, and 2 over 5. The next step is encoding letters as numeric values. To encode a message, we first map letters to numeric values. This mapping is defined as follows. A equal to 1, B equal to 2, and lastly, Z equal to 26. Spaces are represented by 0. For example, the word love is encoded numerically as L equal to 12, O equals to 15, V equal to 22, E equal to 5. This numerical representation forms the basis for constructing vectors used in matrix operation. Well, in this case, our message is we love algebra. So this will give sequence to 23, 5, 0, 12, 15, 5, 32, 5, 0, 0, 1, 12, 7, 5, 18, and 1. So the message matrix is an 8 by 2 matrix because the encoder matrix is 2 by 2. So to encode, we will multiply each 2 by 2 column of the matrix by the encoder matrix. So basically, encoded matrix equals to matrix E multiplied by message matrix. Next step is the decoding the message using the inverse matrix. Decoding reverses the encoding process by applying the inverse of the encoder matrix to the encoded vectors. The inverse matrix is calculated using the adjoint method. We need to multiply E inverse by each encoded vector to retrieve the original numeric values. This value obtained corresponds to the original numerical representation of the message. Lastly, the verification of the decoded result. Verification ensures that the decoding process is accurate. Applying the inverse matrix equals to E inverse multiplied by the encoded vectors, which will give us the matrix messages, which is the original matrix messages. We will need to repeat this for all encoded pairs in order to reconstruct the original messages, which is we love algebra.
Today, we are going to learn about encoding message using a 3 by 3 matrix. This involves the application of matrices where we focus on two key operations. The first one is finding the inverse of matrices using the elementary row operations ERO method, and the second is multiplication of matrices. This method provides a secure way to encode and decode messages. To encode a message, we first define two matrices. First is the encoder matrix A, which is a 3 by 3 matrix used to encode the message. The second is the decoder matrix, which is the inverse matrix of matrix A and is used to decode the message. So, to define the inverse matrix, we use the elementary row operations ERO method. As shown here, the process involves converting matrix A into the identity matrix on the left hand side while simultaneously transforming the identity matrix on the right hand side into inverse matrix. By performing these operations, we arrive at the decoder matrix, which is the inverse matrix is 3 1 1 1 2 0 minus 2 2 0. This matrix will be crucial for decoding the message letter. Next, let's encode the message. The plan is ready. We we represent the message numerically, where each letter corresponds to its position in the alphabet, which is A equal to 0, B equal to 1, and spaces are represented by 26. For this message, the numerical representation is 19, 7, 4, 15, 11, 0, 13, 8, 18, 17, 4, 0, 3, 25, and 26. We organize these numbers into a matrix suitable for multiplication with the 3 by 3 encoder matrix. Encoding the message, which is metric multiplication. Here, we multiply the encoder matrix A with the metric representation of the message to produce the coded matrix. The encoder matrix is, which is matrix A. Our matrix A is 1 over 5, 1 over 5, minus 2 over 5, 1 over 5, 1 over 5, 1 over 10, 1 over 5, minus 4 over 5, and 1 over 10. The missing matrix contains columns of the numeric message. By performing matrix multiplication, we get the coded matrix. For the coded matrix is 18 over 5, 26 over 5, minus 3, 21 over 5, minus 5, 28 over 5, 29 over 5, 6, 21 over 5, 8, minus 7 over 5, minus 29 over 5, minus 2, 1 over 5, and minus 60. This coded matrix represents the encoded message, make it unreadable without the decoded matrix. For decoding the message, to decode the message, the receiver uses the decoder matrix, which is matrix inverse, to multiply it with the coded matrix. This process reverses the encoding, restoring the original numeric values of the message. Once decoded, the numeric values are converted back to letters, revealing the original message. The plan is ready. For verifying the process, to ensure the encoding and decoding process works correctly, let's verify it. First one, start with the original message matrix and multiply it by the encoder matrix A to produce the coded matrix. Second, use the decoded matrix, which is inverse matrix, to multiply with the coded matrix. If everything is correct, the final decoded matrix should match the original message matrix. This confirms the accuracy and integrity of the encoding-decoding process.